Okay, off we go. So today's a fun one because it's about graphs. For some reason, I assume graphs are always more fun. Uh, what we have done very recently, just last week, Monday we did dimensionality reductions. That was this idea of trying to take some structures like distances and put them into a simpler structure, like lower dimensions. Yeah. And in building off that, we did locality sensitive hashing. This was sort of a plot twist on hashing where we actually wanted collisions, right? The idea was to try to set up some kind of hashing scheme where nearby points are more likely to collide. So that if you want to do the nearest neighbor, you basically just do some table lookups with some amplification. Okay, so very nice idea. So today, we're really talking about the sparsest cut problem. And to do that, we'll have a nice technique called L1 metric embeddings. So, okay, let me actually introduce what the two results are first to set the picture, and then we'll go back and we'll do the proofs. But so last time we did this result, which if you haven't seen it before, is a very maybe different style of result, right? Because we took some high dimensional, potentially complex thing and showed we can always embed it into log n dimensions while roughly preserving the underlying metric. And so with that in mind, so that was for the Euclidean metric in particular, right? We're preserving the L2 norm. We're going to look at different metrics today. Today's point of emphasis will be the L1 metric. Okay, so you have two vectors, with various coordinates. And now instead of looking at the sum of squares, you're looking at the sum of absolute differences. Okay, which for many of our applications is actually more general, right? Many of these combinatorial or optimization settings, we're really doing some kind of sum, not sum of squares. So of course, that's one of many possible metrics. So for example, you have L2, L1, L infinity. What does a unit circle look like in L2? Okay, just it's a unit circle. Okay, what does a circle look like, so to speak? All the things in distance 1 for L1. Survey says it's a diamond. Uh, Arguably a square. But anyway, what about L infinity norm? Yeah, it's a square, or arguably a diamond. Okay. Um, Fine. Yeah, okay. So different metrics have different characteristics. Today we'll focus on L1. And what we'll prove and also learn how to use uh, is the following amazing theorem. Okay. It says that you can give me any metric. Okay, and I want to stress any metric. It doesn't have to start in Euclidean metric. It doesn't have to start as a L1 metric. Give me any metric, and I can give it coefficients. In this case, log square and coefficients. Okay, and if I look at the L1 norm induced by this embedding, so I take any metric. It could be a shortest path metric, right? So you have the shortest path. You have vertices in some undirected weighted graph. So that induces the shortest path metric. That's some kind of metric, right? And I could take all the points and assign them some kind of vectors so that the L1 metric will preserve the original metric up to a logarithmic factor. Okay, so you can take a shortest path, not at all explicit metric. You can just give me the metric, even in terms of its pairwise distances. There's no particular location. And I can always embed it, in some explicit representation. L1 norm was log n stretch. Okay, so to be a little bit more specific, none of the distances will shrink, and they will expand by at most log n. Of course, we could scale down and say they'll never expand and it'll shrink by at most log n. So all that really matters is the product of the two. Either case is log n. Okay. All right. So those are the two. That's one main result, and then the other thrust of this lecture has to do with graph problem called Sparsest cut. So here's first. There's a picture coming up. But let's see. So you're given an undirected graph with edge capacities, okay? And actually, let me go to a special case first, because I think it's easier to understand. So this is very natural if you want to start doing kind of divide and conquer on a graph, okay? And the high level idea is you want to kind of divide the graph in half. You want to remove a few edges and have most of the graph surviving with large chunks so you can do divide and conquer. Now, if you do like just a minimum cut, which you might do based on just like regular algorithms, the minimum cut in a graph like this is just going to trim off a leaf, and you won't make much progress from a divide and conquer point of view. So a different objective would be this notion of sparsity. There's a couple of notions of sparsity out there, but we'll focus on this one today. So in the numerator is the number of edges in a cut. Okay, so S is a set of vertices, and this is the number of edges cut. Okay, and this is the number of vertices on one side, and this is the other side. Okay, and now when you're taking the product of two things, you're dividing into two parts and taking the product of their sizes. What maximizes this and what minimizes it? At some level, if I want this ratio to be small, which means I want the denominator to be big, am I looking for S and S bar to be roughly equal or more lopsided? Of n vertices, say, which equal, right? So if I have 2 halves of n over 2, you get like n squared. But if it's n times 1, you just get n. So now when I try to minimize this ratio, I'm trying to remove as few edges as possible. That's the numerator. But in the denominator, I'm still trying to actually get things somewhat balanced, right? So multiplying S and S bar together um, is going to prefer more balanced partitions to unbalanced. Okay. So like in this kind of toy graph, what would be maybe a good sparse cut? Yeah, so something like this. Okay. And as it turns out, being able to do this well is a very useful primitive for any number of problems. For example, a different problem is you want to minimize, say, cut S subject to exactly half the vertices on each side. Okay, so a perfect bisection problem. You can use a good algorithm for sparsest cut to approximate this problem. You actually get a bi-criteria approximation where maybe you can guarantee each side has at least n over 3, and you're within some competitive of the best bisection. So it's a little bit of a funky approximation, but the algorithm is based on kind of you do the sparsest cut. If it's already really balanced, you're happy. Otherwise, one side is much bigger than the other, and you get another sparsest cut in the bigger side. And you just keep chipping away at the bigger one until you can kind of reassemble a balanced cut. Okay? So, and it's sometimes used for flow. It's useful for a number of things. We'll get the approximation ratio for this sparsest cut in a moment, but that approximation ratio kind of maps onto the best approximation ratio for a number of approximation problems out there that are really driven by this divide and conquer kind of graph partitioning approach. Once the graph gets small, it's easy, Okay, so it's high level. Now we'll do a slightly more general uh, formulation where the only difference here is the denominator. And so what we've done is we've kind of assigned a score to every pair that gets split up. Okay, so here you want some B. Okay, so this could show up in like some kind of network setting where certain pairs of clients are maybe more important than others to separate. But otherwise, you're trying to minimize the numerator divided by this kind of weighted score. How does this map onto our kind of uniform setting? Sorry. If B is always 1, if this is always 1, sorry, if B is always 1 everywhere, then this whole sum would just be multiplying one side with the other, because every connection is worth exactly 1 point. Okay, so that's why this version is called uniform sparsest cut. It's when all the pairs are treated equally. But what we do will work for the more general setting. All right. So okay. So those are the two main things we're going to get to. Okay. But as a warm up, we're going to do something that hopefully most of you have seen before. Yeah. So max flow min cut. Has everyone seen? Has it? Well. Uh, if I said it, has anyone not seen max flow min cut? You won't want to raise your hand. But okay. So max flow min cut is often covered in algorithms classes. I'll give a brief warm up, but not too much detail. But some level, you can ask a question like, I know some of you have seen the slides before. Given S&T, how well are they connected, right? And you can ask any number of questions. Oh, okay, sorry. Here's the usual thing. This was actually partly motivated by operations research, which is a kind word for Cold War. And at some level, here's a map of like Russian railroads. And you're like, well, in the event of escalating war, how can you make the most disruptions to the railroad network with as few uh, bombs of all those? Oh, this is Jeff Erickson's notes from UIUC. Yeah, in my other class, I often refer to his notes. He has excellent exercises. Uh, Connectivity is also useful for CPUs. Of course, you want parts of the CPU to be connected. There's lots of network design problems. Social networks, how well something's connected is for like how good you are as friends or something, blah, blah, blah. I'm going through this quickly. People also analyze the network of the internet. Okay, so there's any number of ways to kind of measure connectivity. Let me just get you to the list because we won't go as slowly as the usual lecture. You can ask questions like, can S get to T? How many different ways can S get to T? How many ways can you go from S to T using, say, 5 edges, 6 edges, right? These are all natural questions. Many of them can be solved. Some of them can't be solved. What's the shortest S to T path? Something that's shorter might be a stronger connection. That's like latency. How many shortest S to T paths? You can actually do this. Here's another question we'll eventually come to. If you did a random walk starting at S, what's the expected number of steps until you reach T? Okay. And in the last two questions I want to highlight, what's the maximum number of edge disjoint paths from S to T? That's the max flow question. What's the minimum number of edges you need to delete until S can no longer get to T? Okay. Okay. So, all right. So that first question, which is really max flow, is a packing question. So at some level, I'm thinking of trying to fit as many S to T paths as I can into the graph. Okay. Uh, and every time I take a path, it sort of uses up all those edges. Okay, so I'm packing. I'm trying to fit something in. Okay. And the minimum cut problem, okay, I'm trying to remove some edges that disconnects S from T. I can think of that as a sort of dual covering problem. Because for every path that goes from S to T, I have to take at least one edge. Okay, so just like set cover from before, now the sets kind of correspond to the edges. I'm kind of trying to cover the path by making sure I take at least one edge from every path. Okay, so in that sense, they're dual to each other. One's getting packed into the other's getting packed into the first. Okay, and whenever you get a packing and covering kind of setup, you get an inequality like this for free. Okay, the maximum number of S to T disjoint paths is always bounded above by the minimum number of edges in any S to T cut. Does anyone want to take a shot at proving this? So every path, let's say you have a bunch of edge disjoint paths. Every path needs at least one edge from this cut because the cut needs to take. Okay, fine. And you need one more observation. Yeah. Yeah. So every path has to go through this cut. So the cut will have at least one edge from every path. It might seem odd, but we need one kind of keyword. Yeah. Yeah. Okay. So I want to show the number of edges is at least the number of paths. There's only one keyword that we kind of haven't really used. Disjoint. So each path has at least one edge from the cut, right? But they're also disjoint, so these are different edges from the cut. So that you need to make sure the one size is bigger than the other. Okay, so it's not too difficult. But also that argument is very generic. There actually wasn't that much to do with paths and edges. Okay, so the real question is whether they're equal. Of course, many of you have studied this before, so you kind of know the answer. But what we're going to do today is we're going to do a different proof. Okay, so we're going to do a proof based on LP duality. We've done LPs a little bit before. Okay, here's some warm up. I think you're kind of used to this notation. I don't know if we've done the transpose before, but that means you kind of rotate the matrix over. Okay. All right, so good. Here's the LP duality theorem. Okay. Suppose you have any packing LP, which I'll describe as follows. Any LP of the form maximizing some linear objective subject to some packing constraints, ax less than equal to c. I can only take so much of x because of all these capacity constraints. Okay, so max bx subject to ax less than equal to c. And there's always an associated dual covering problem. Okay, now I'm going to minimize cy, where I have y needs to be big enough to kind of meet these covering constraints. Some convex combination of the y's has to be at least b1. Some convex combination of the y's has to be at least b2. Okay, and that packing and covering incidence is related by the transpose. Okay, so the packing matrix here is transposed here. That's why you'll see the dimensions got swapped between x and y. Okay, so whenever you have that set up, the LP duality theorem says their objectives are exactly equal. They're always equal. Okay. Whenever you have this packing, you can derive what the covering is, and they're equal. And then one thing that's very nice for many problems is that maybe you're really focused on this problem, but somehow it may still be helpful to look at the dual and study this problem, and also work with a solution to this problem, which can give you hints towards this one, because they're really two sides of the same coin. Okay. Today, all that, yeah. No, definitely not positive definite. And they don't even have to be non-negative. Yeah, they're not. They tend to be non-negative in our ideas. Yeah. I think in this version it's okay, but yeah, you might. You, in some, so depending on how it's set up, you might need to be concerned about whether it's finite or not. In this case, well, so in this one, there's always a feasible. Oh, okay. Okay, yeah. Let's assume it's okay. Just assume it's nice or something, and I'm not going to worry too much about this. Okay, it's not too important. Okay, but let's apply this to Maxwell min cut. Okay, so we can take that path packing. I'm just trying to stuff paths into the graph, and I can write an LP. Okay, so this is just a fractional version from before. It looks messy, but it shouldn't. It's not intended to be complicated. Now I can take 0.1 of a path, 0.2 of a path, 0.3 of a path. I can take any amount of a path I want. It's got to be non-negative, but that makes sense to us. Okay, and then here are capacity constraints, right? This edge is capacity 5. If I look at all the edges using that edge, all the paths using that edge, yeah, 0.1 of this, 0.3 of this, 0.7 of that, it can add up to at most 5. Okay, so you're just packing. Okay, and if you write the covering LP, right? So covering LP, I want at least one edge from every path. So we're going to relax that to now instead of taking an edge, I'm going to take a fraction of an edge. Okay, I'm allowed to take 0.2 of an edge. And instead of saying you have to take one edge from a path, the continuous kind of version of that is to say, well, if I look at a path, the sum of the amounts you're taking needs to be at least 1, right? So if this had to be integer, then it would be saying you have to take at least one edge. It's fractionally saying you have to take at least one edge from every path. Okay. And LP duality, if you look at this incidence structure, right? E and P, P contains E, they're all 0, 1. So they really are A and A transpose, the exact same incidence structure. Okay, it's just that the variables and the constraints, the rules have been swapped. Okay, so they are dual LPs. Okay, so LP duality will tell us that these two LPs are immediately equal. Okay, now the left-hand side LP is exactly the max flow problem that you've seen in class, which is often described by, kind of sending water from S to T. This problem is a little bit weirder. This is not clearly going to get us a solution to min cut, right? So there's some kind of rounding issue over here. Okay, so what do we know? So LP duality, just by looking at the LPs, you know that max flow is equal to some kind of min fractional cut. Okay, but it's not the max flow min fractional cut theorem, it's the max flow min cut theorem, right? So we want to somehow, show that, right? And we know that since this LP is a relaxation, the min fractional cut, that value, whatever it is at most a min actual discrete cut. You have to actually take edges. Okay. And what we want to show is equality or greater than equal. And then we'll have a kind of LP-based proof of the maximum min cut theorem. Okay. All right. So what we're going to do is we're going to take a rounding approach. Okay. So we're going to solve this LP on the right, right? There's some solution. And then we're going to figure out how to turn it into a discrete cut. Okay. So, all right. So suppose you have some LP solution, maybe something like this. So if I did this correctly, probably didn't, every S to T path should have total distance at least 1. Yeah. I assume if there's something wrong, somebody would have pointed it out years ago. Okay. But we're assigned fractional values to all the edges here. I guess we're just assuming all edges have cost 1. And uh, and every path from S to T should have total length 1. Yeah.
Then LP have like exponentially many conditions.
Yeah. Okay. So this is a great point. Yeah, there are exponentially many constraints. Okay. Now, slight aside, there is an algorithm for LPs called the ellipsoid algorithm. Okay. For time constraints, I won't go into exact details, but at some level, it can let you handle an infinite number of constraints, but it has the following requirements. So at some level, the ellipsoid algorithm will kind of start as if there were no constraints. And it'll start with some solution. It'll probably start with y equals 0, because that's feasible if you ignore all this, and otherwise it minimizes the capacity, right? And now your job, given some y, is to find one violating constraint. Okay? So ellipsoid algorithm, you have to be able to provide a subroutine that finds a violating constraint. So in other words, although there's exponentially many constraints, there's so many paths from S to T, right? So we wouldn't be able to just write this LP down and feed it to the computer. That's the basic issue. So ellipsoid is going to be able to deal with this implicitly, but what the ellipsoid algorithm says is like, okay, I have some candidate solution Y, but I can't check all the constraints because I haven't written them all down. Can you find me a violating constraint? So as long as you're able to program a subroutine that given Y will find a violating constraint, that gets plugged into the ellipsoid machinery, which is sort of a high dimensional geometry argument based on something called the John's ellipsoid algorithm. Okay, but it will converge in a polynomial number of these violating constraints called cuts. You will get an optimal solution. Okay, so let's address that now. Suppose you have some tentative solution Y. Okay, and now you need to validate these constraints. There's exponentially many. Okay, so you need to either figure out that Y is feasible, it satisfies all these constraints, or just output a violating constraint, right? One of these paths where it's not satisfied. So how can I implement this oracle for the ellipsoid algorithm in this particular case? So I give you some set Y, some fractional solution, there are values on all the edges. You just want one violation, yeah. We'll find the shortest path from S to T. If it's at least 1, all the paths have distance at least 1. If it's less than 1, that one path is a violating constraint. Okay. So to actually solve this LP exactly with the ellipsoid, you'll just repeatedly do shortest path computations and feed that into the ellipsoid algorithm. Okay, and then the machinery will take care of the rest. All right, good. So in any case, also to prove the Maxwell min-cut theorem, you don't even need an algorithm, right? Just as the existence of a solution is fine. It's just a mathematical theorem. Okay, so let's say you have a fractional solution. Now I want to round it into an ST cut, right? This is some kind of fractional ST cut. I want to round it. Any ideas?
Maybe you change the values in probabilities.
Sorry?
Use the value that you got as probability.
Okay, so I can treat each edge being like a randomized rounding. Maybe I can just like scale up and round. So if you when we did set cover, we did have to scale up, right? And if we didn't scale up, we probably would miss them because only constant probability would hit a particular path. And it seems like there's multiple paths here, so you'd have to scale up to take some union bound. Now, one obvious issue is that there's exponentially many paths. It's only taking a union bound over that may require scaling up a lot. But another basic issue is that I want to be able to round this without any loss, right? Because I want to prove Maxwell min-cut exactly. So I want to get a solution where I don't lose anything, and the moment I scale, I'm losing something, let alone the fact that you might have to scale up a lot. Okay. Uh, so that won't quite work, but it is a natural idea. That's how we rounded 1LP before. Any other ideas? Hard to guess, but it's fun to try. Yeah.
Could you do like an augmented kind of thing where if you're out something down, the same one is on.
Uh, can you do an augmenting pass style thing? Uh, I mean, obviously you can just run Ford Fulkerson and get the theorem another way, but that wouldn't have anything to do with the whys. Uh, yeah, I don't like to say you can't, but it's certainly not the approach I had in mind. Uh, okay, how about a hint? Okay, step one. I'm gonna embed all the vertices on the line based on their distance from S. Right, so I'll just run, Dijkstra's algorithm starting from S or something. This vertex is zero point 0.1 away. These three vertices are zero point 0.2 away, so on and so forth. Whether it's accurate to the previous picture, I'm not sure, but okay. So I can embed them on a line from S, and a key point is that T will be at least 1.0, right? Because the distance to T had to be at least 1. In fact, it's probably going to be exactly 1 because the solution will be optimal. Yeah.
It's not the LP because really it's just like less than
Less than equal to 3?
it's not the LP sum should be less than right? The discrete cut.
Oh, you're worried that this solution here might not be optimal? I'm sure. I made it up. Yeah, that's probably true. Uh, yeah, yeah. Small human brain can only do so much. Okay, but imagine I had laid it out as thus. Okay, and I want to round it without loss in any case. Okay. So any ideas from here? I want to output a cut from S to T. Yeah.
Number and cut all the edges.
Okay, so I can try pick a uniformly random number and cut all of the edges less. Okay, so that means so I would cut this edge too. Okay. No, that's an idea. So like okay, that's fine. So let's let's look at this edge I've drawn an arrow to. I'm going to draw it in another color. Okay. So I'll pick a random point on the line and I'll just cut everything to the left. Okay. So like in this particular example, which is not an optimum solution, it probably doesn't even reflect the previous graph. What's the odds of me including that edge in the cut?
Six.
Yeah, I guess anywhere beyond here.
If you like, I thought I would cut the edges.
Ah, okay, well, that's a different algorithm. So the first suggestion was that we cut, if I drew the line here, just all the edges to the left get cut. And that's one possible. You had a different idea in mind, which is if I draw the line here, then instead I would cut. Yeah, in other words, I would take these vertices on one side of the cut and those vertices on the other side of the cut. And this may be a little more natural. So we'll just split the vertex set in half, and whatever edges happen to be cut, then they'll get cut. Yeah. So that's what we'll do. We'll pick a random number uniformly at random. Okay. And this will just go somewhere, right? And that will cut these three edges in that case. Okay, that would just be a singleton cut with T on the other side. Okay. All right, so let's analyze this. Okay, so you pick one and you output the cut at this angle. All right, what's the expected capacity of the cut? That's what we're interested in, right? What should we do first? It's a natural first step. Yeah, what's the buzzword? Okay, we'll do some linear expectation, something like this. Okay. Now, what is the probability of this edge being cut? Remember, at some point we have to relate it back to the LP. Sorry. Yeah, so it's really the distance from B to A, right? Okay. Now, how can I relate that to E's LP value? Is it just YE? It's not necessarily exactly YE, but it's how are we going to relate it to YE? Might not be equal, but it's certainly we can say something about YE. Remember, this is the shortest path stuff, right? Nothing to do with binomials. It's just so how can I relate the length of E kind of along this line to YE? It's not necessarily equal, but you could still say something. Less than because? Yeah, so if YE was smaller, then B would be to the left. So I know that B minus A is at most YE. It'll probably be equal in the LP solution, but in any case, it's at most. Yeah. No, YE is the LP solution, but then A and B were laid out based on the shortest path from S. So A to B is taking the actual placement of B is based on some shortest path starting from S. All right, good. So that's where you get the CEYE, and that's our LP solution. Okay, so a random cut in expectation is going to be very good, right? Okay, good. Now, how can I show that there always is a cut, right? We're trying to do a math theorem here. One last kind of swift punchline.
Expectation, it's smaller than at least one for one of the random things we're taking the expectation of. So.
Yeah, so if the average is good, then something has to be good, right? If you found out that the midterm average was like 95, you know, at least somebody in the class got 95. Okay, so why isn't this working? Okay, something like this. Okay, so just because a random cut is good with probability greater than 0, there is a cut. That's good. And that cut will be your min cut. Yeah. In fact, how can you actually find, because some of that probability could be very close we haven't said anything about the probability, right? So how can you actually find this cut that's as good as the LP solution without running Ford Fulkerson, right? What was the point of this whole exercise? I want to actually find, so we know there exists a good cut because the average is good. Okay. And how can I actually find it?
Shouldn't the less than or equal to be greater?
Uh, I'm a little confused. Oh, well, okay. No, because this represents the LP. This is the LP value, right? And we just were able to show that the average, right? So that it represents this minimum capacity of any fractional cut. So that's okay. Okay. All right. So the average cut is good. Some cut must be good. How do I get some good cut? Yeah.
You get like the conditional expectation given you take a certain cut versus not a certain cut. Sort of like, so you pick whichever one's smaller.
So conditional expectation is really helpful when you're making a sequence of decisions, right? Because you can play out the expectations, kind of simulate the average in the future. But here there's not a sequence of decisions, it's just one decision. The only thing is that it's a bit of a needle in a haystack, right?
Sort the you could do that to sort the vertices by distance, and then the decision would be whether or not it's bigger than.
Maybe, well, no, well, it's simpler. Yeah. Well, we don't have any guarantee about how often you'll get it, so we don't know how many times you have to repeat. But there's a simple, direct way to do this. Yeah. Yeah, just sweep through, try them all. There's only a few interesting ones, right? There's only an interesting ones. Okay, so you'll find it. Okay, so what did we show? Okay, so we use this kind of probabilistic line embedding argument to show that any fractional ST cut can be rounded to an ST cut, a discrete one, right? Without increasing the value. And then this last thing you get for free from max flow. Okay. So at some level, if you're very comfortable already with LP duality and linear expectation or something, then you don't have to go through all this Ford Fulkerson stuff. Yeah. It's at least mathematically more direct. Okay, simple enough. All right, so that would be an alternative theorem, a way to prove max flow min cut. Any questions? Yeah. Which one's faster?
Yeah, like the LB or the.
Well, this LP will work even with real capacities, and Ford Fulkerson will never terminate, right? So some ways this will win, other ways it won't. Yeah.
By solving the LP, we get fractional values. Then, how do we make it with things like that?
Oh, yeah. So the algorithm will choose a random theta, and then whatever the cut, think of it as vertices on one side or the other. Here's the S side of the cut, and there's a T side of the cut. That means these are the edges getting cut. So that's your discrete set.
The actual edge capacity.
They don't have to be integers in this. Those are just given the costs here, right? We don't need this value to be an integer. Okay, good. All right, other questions? Yeah. So you know that there's some choice of theta that works, but there's only a few interesting ones, right? The one between the S and the first vertex, and between the first and second vertex, and second and third. So you can just try them all. Yeah, there's only n interesting distinct choices, or n minus one or something.
I can do the average stuff just to make sure that there is a choice that will.
That's right. That's just on the back end analysis. Okay. All right, let's keep going. All right, so now coming back to sparsest cut and L1 metric. So you'll see the connection in a moment. Okay, so sparsest cut again, you want to not cut too many edges, but roughly break the graph in half. Okay, so we're going to take an LP-based approach. Maybe inspired a little bit by this max flow stuff. So the first thing we got to do is figure out how to write an LP or sparsest cut. Right? Okay, what's at least awkward if you want to try to turn this kind of choosing S and stuff like this? What's one thing maybe awkward about sparsity from a linear program point of view? Or maybe the ratio is an issue. Yeah.
Research and like multiply by the denominator.
Eventually, yeah. Okay. All right. Okay, this sort of has taken us off the rhetorical railroad tracks. Okay. So maybe here's an interesting idea. So maybe the first basic question is like, how do you even come up with a continuous way to model cuts? Okay. Turns out the one answer is a metric. Okay. The reason is that you can always think of a cut like this. Okay. You can define a metric where if two vertices are on opposite sides of the cut, they have distance 1. And here we're going to use metric a little bit loosely. If they're on the same side of the cut, they have distance 0. They're allowed to have distance 0. That's the only difference from regular metric. Okay. So this will be distance 0. But something like this is called a cut metric, will satisfy a triangle inequality, and it's also undirected, symmetric. Okay. And you can do this, you can lay a bunch of sets on top, right? You can put another set there where this is 1 and that's 0. Okay. So you can have a sum of these cut metrics. Okay. So a natural way in a lot of these graph problems to continuously relax and model cuts is by say, oh, give me a metric. Okay. So in this LP, instead of worrying about putting vertices on one side or the other, I'm going to be worried about creating a metric that assigns some kind of distance between each vertex. So having distance 1 is sort of like putting it on one side or the other, but it's a little bit harder to interpret. But in any case, so DUV, right? So 1 if they're on separate sides of the cut, 0 if they're on the other, on the same side of the cut, would be one example of these. Okay, so let me make this a little bit more clear. So in other words, given some candidate solution S, because it needs to be a relaxation, right? Given some set S, we can define a metric, I'll call it D sub S, where D sub S UV is equal to 1 if UV is on the same side of S and 0 other side. Yeah, on different side. On different sides and 0 if they're on the same sides. Okay. And if I took that D and plugged it into this ratio, you'll get the exact same score as up here. Okay, because it'll be exactly the edges that are cut that get a 1. Okay, and things like this. Okay, so we're gonna replace this whole like choosing one set with a metric. Yeah. Well, I'm introducing variables. So what the LP is going to try to do is it's going to assign values d, u, v greater than or equal to 0 for all vertices u and v. and it's going to have to satisfy the usual rules of a metric. So it needs to be non-negative, it needs to be symmetric, and it needs to satisfy the triangle inequality. And the one thing nice about a metric is those rules are linear inequalities. So I add that to the LP. So when I'm writing this kind of over metric D, so the LP is trying to choose a metric, and that's really a shorthand for explicitly writing out the rules of a metric that the LP needs to follow. It needs to be a triangle inequality, it needs to be symmetric, it needs to be non-negative. Okay. Good. So that's the first idea. The next issue is just that if we want to do an LP, it can't be a ratio of two things, right? It should be some linear objective subject to some linear constraints or something. Okay. So this was already suggested. Can you deal with a ratio? Sorry? No, not logarithms. Well, then you lose linearity. Yeah.
You can just like look at all the different possible combinations of the different set personalities.
Well, not necessarily. So if you imagine you knew the optimum value, suppose I gave you the optimum value. Then, right, if you had the optimum value, is that erase here? Okay. Well, okay, but actually you don't really need to binary search. You can flatten it out by just saying, because it's scale invariant, right? If I doubled the metric, I doubled everything. Numerator goes up by 2, factor of 2, denominator goes up by a factor of 2. So it's scale invariant. So if I just, instead of doing any binary search, I just said, well, the denominator has to be at least 1. Otherwise, minimize the numerator. That's like sort of taking a scale invariant thing and just fixing a scale. Okay. So by just saying, okay, denominator has to be at least 1, then the numerator will recover opt. Okay. So now what does this LP look like? It's saying, okay, it's sort of some kind of like minimum cost metric. So the metric needs to be spread out. The sum of distances weighted by B needs to be at least 1. But otherwise, you want to minimize kind of the cost of these distances.
Why don't you second equal to?
You could. Yeah, no big deal. It doesn't matter. Okay. I think I like this just because it keeps it as like a covering LP. It looks a little bit more like the covering from before. Okay. Good. So we've come up with an LP for sparsest cut. All right. Okay. Next question is, how do we round it? So I can plug in to solve this LP, and it'll give me some metric, okay, satisfying these things. But now I wanted to actually take that metric and turn it into a discrete set of edges. Make sense? Any ideas? We have lots of hints coming up, so you don't have to have ideas.
You do the same thing as before, where you get the shortest path.
Okay, so can we do something like shortest path? Now, if you do shortest path, where do you want to start the shortest path?
Any two vertices.
From 2 vertices?
Yeah.
Well, shortest path starts from 1.
Yeah. You're starting at every single vertex.
Okay. Okay, well, yeah, okay, so let's try something sort of in the same spirit. Suppose I told you that the distance metric, for a magical reason, was particularly convenient. Okay, that it was induced by a line embedding. So what does that mean? That means that there exists some kind of assigning every vertex to something on the real line, and that the distances were kind of the distance on the line between them. Okay, that's of course not generally the case, but building up to stronger ideas, suppose that was the case. And then what could we do? Or what's the pattern matching thing to do? Yeah, so maybe we can pick a cut uniformly at random. Okay. Now what happens when you do that? Okay, let's analyze it. Right? Okay. So the expected number of edges that are cut, I guess S sub theta is, whatever is on the left side for a particular value of theta. And then what was the first step again? Is some linear of expectation or something. Oh, that's the wrong one. Sorry. Going to linear of expectation. And exact same as before. Okay, I know the probability of it being cut, is sort of that space on the line. So that's the distance between the two endpoints. Okay. And then now I want to figure out the denominator. Okay. So that's also doing some linearity of expectation, just like before. Okay. So nothing special. So the only difference maybe from before is that we have a numerator and a denominator, not just a numerator, but the analysis is the same on both sides. Now, okay, so this is good, right? To some level, what have we shown? So we know that this divided by this, the two right-hand sides, that's opt, right? That's the original LP opt. So we've shown at some level that the expected size of the cut divided by the expected kind of spread or whatever is optimal. Are we happy? Yeah.
Define the expected values like that.
Well, this is just right now. This is just a fact coming from the fact that this is exactly equal to this, and this is exactly equal to this, and this divided by this is exactly equal to opt. So at this point, we haven't cheated. But what's the issue? Exactly. So this is the ratio of expected values. And what I'm really interested in is the expectation of the ratio. Okay, so good. So that's not actually the expected sparsity of this cut. That's expected ratio of this cut. Okay, but how can I fix this? Not sure if that's actually, no, not what I have in mind at least.
Wait, do S and T denote the sink and source, or are they just any?
No, this is just like enumerating all versus S in one side and T on the other, and you get this many points if you split them apart.
So that sum is at least.
Well, in the LP, we sum this thing is at least one. In truth, what we want is the expectation of this divided by this without. Okay, so how do we sort of flatten this out? So we only need this in analysis. So suppose, okay. Okay, so I'll call this like lambda or something. Okay. So now if I instead look at the expectation, or let's look at this. Let's look at C delta S theta. So this is the number of edges we cut minus lambda times of all the pairs that we cut. BST. Okay. So some level I've just kind of flattened it out. Okay. And now if we look at the expectation of this thing, and we do the same analysis as before, which would immediately take them apart, right? What would this thing be? This thing would be less than or equal to 0. Okay? Just by how we chose lambda. That means there exists theta such that C delta S theta is less than or equal to lambda times the sum of BSTs, right? And then you finally get that, this ratio, blah, 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 is at most lambda, and now you're happy. Okay, so exists a cut, you just have to flatten it out first. Yeah. Yeah, so we can do this a little bit more slowly. So you'll get this, an expected value of that. And then if we look at how lambda was chosen, in other words, imagine I had multiplied this out, and then that means this is equal to this. Yeah, in fact, it would be equal to 0. All right, simple enough. So yeah, so this awkward ratio of expectations, you can actually just get around. You just have to linearize it in the analysis. And as soon as the expectation is good, now you can just find it by scanning the thetas. Okay, good. Making okay progress. All right, good. Now, all right, so okay, that was a very nice case where it happens to be a line embedding, and then we can kind of do something very similar to Maxwell min cut with that one adjustment to account for the ratio at the end. But it's actually the same algorithm, just the analysis require one more trick. Okay. Now, okay, now as the next step, suppose I told you it's not on a single line, some of it's on many lines. So suppose I told you that D was an L1 metric. That means that there's some embedding, every vertex is assigned some location, and their distance is given by their L1 norm, right? The absolute value differences, which you can think of as having a bunch of line embeddings and summing them up or averaging, however you want to think of it. Okay. All right. So, suppose, right. Okay. Now suppose your metric was an L1 metric. Then what could you do?
Put each one separately.
I think ultimately that may be what we do. Okay. So let's think of this way. All right. So, okay. Then if we kind of do the exact same analysis from before, right? So this is DUV, right? So we have this. This is just exact same analysis before, but I've just kind of plugged in, our DUV is now the sum of terms, okay? And otherwise, we've kind of quietly interchanged sum. So originally in the L1 metric, the sum would have been inside, but I pulled it outside. The sum over all the coordinates would have been inside, and I've already pulled it outside. Okay, so this is true. This just builds on what we just did. Now what? We will not need to use the triangle inequality. Then this lambda kind of represents the best possible ratio, right? So we know how to deal with one line metric, and this says that kind of many line metrics in the aggregate is very good. And you know what to do with one line metric. Pounding energy drinks. So we know that one line metric we can round without loss. And this is saying, look, you have a sum of line metrics that's very good. How can we round it without loss? Right? Like each of these i's represent one more line metric, right? Okay, but why would that work? Yeah.
Just move the lambda. So
Yeah, if that helps, you can move it inside like that. So what's it saying, right? You know that at least one of those i's, for at least one of these i's, this must be true, right? They can't all be bad because in some they're good. So there must be at least one that gets you this wonderful inequality. Okay, so there's some I that's also good. So as soon as many i's are good in the aggregate, at least one of them are good. And now you can do the line embedding for that particular eye. Yeah? Make sense? Okay. So you can not only, yeah.
In the first place was depending on it's able to be like a line.
Well, it really represents also, so this also coincides with LP opt. Because so we already showed those two were equal, and the ratio of these two, that gives you the LP opt. So they're all kind of the same here. Okay, good. All right, so you can now round L1 metrics. Okay, good. So L1 metrics can be rounded without loss. In fact, they're no harder than a single line metric. That tells you something about why L1 metrics are useful. Okay, good. All right, now here comes the big question. How do you deal with general metrics? Line metrics you can deal with, L1 metrics you can deal with. What about in general? Quick. Okay. So we can take any metric and we can embed it in L1. Now we're going to go back to that statement. I mean, you probably forgot from the very beginning of this lecture. So the very beginning we said, look, you can take any metric, right? It requires nothing about the metric, and you can always embed it as an L1 metric and give up a log n factor. Any metric can be embedded in L1 and gives up a log n factor. Okay. And then once you do that, so what does that mean? That means the numerator might go up, the objective might go up by a log n factor because things are stretching out. You'll still meet the recovering requirement because things don't shrink. So you can take your general D and then you get a new LP solution that this time is an L1 metric, but you give up a log n factor. And then you round the rest without loss. Okay. Yeah.
The function that mapping D to like buffer full bonds, right? Like circles the bonds.
It's not. So yeah. So this is just saying you can embed it into L1 with log square n coordinates. For us, our rounding didn't even care how many coordinates there was, but just we'll do it in a moment. Our construction happens to use log square n coordinates. It's the cardinality of, yes. Well, yeah, it's a metric defined over a finite set of vertices. And then this n is really just to be able to take a union bound over all vertices. This could be some 1 over delta if you want to show that every pair is preserved with. Yeah. There are continuous analogs of this, but for us, it's fine to assume it's finite. Well, we might as well find it because we have 10 minutes left. Okay, but at least yeah.
Question about data, like the random data. You're trying to data which include
Yeah.
try all the data's continuous.
Well, these are just embedded on the line, right? So there's some smallest vertex, second smallest vertex, third smallest. So you can order the vertices. And all the cuts are either the smallest or the first two smallest or first three smallest or first. So there's only n kind of interesting possible. Okay. Yeah. So once they're ordered on the line, it's not so bad. Okay. All right. So this is maybe the first time. This is a very powerful idea, though, right? It's the idea of kind of very nice structured metrics. It's only you can do a lot with them. So a lot of other problems can be solved with this idea. Okay. All right. So let's try to do this. Try to figure out how to do L1 metric embeddings. Don't want to guess. Kind of a magical result. Yeah, it's really, it goes back to a well-known mathematician named Bourgain in the 80s, although it was made algorithmic in the 90s. Okay, those are from before. Okay, so I guess formally, Okay, so I think formally what we'll do is we'll get log 1 over delta, and it'll just guarantee that for every well, we'll just see what happens. Okay. All right. I mean, it'll be kind of clear what the result is from the theorem. Okay, so this is actually a very simple metric. Okay. So what you're going to do for each of your coordinates is going to be something like this. You're going to choose some probability, maybe it's like half, for example. You'll do different scales. So let's say half. You're going to sample half the vertices in some set S. Okay, this is just to generate one coordinate of your embedding. And then for every vertex, I'm going to say, okay, how far am I from my random set S? That means everyone in S is distance 0. And everyone else could be a little bit further. Okay. And then we're going to do that for, various different sizes of random sets. But otherwise, it's like very simple. Random set, measure distance from random set. This is called a Frechet embedding, Frechet coordinate. Presumably, there's somebody named Frechet out there. Okay. So what we'll end up doing is we're going to do this at every scale. Okay. So I'm going to first maybe sample everyone's probably 1/2. That's one random set. Probably 1/4. That's another random set. Probably 1/8. Another set. 1/16, 1/32, all the way down to 1 over n. Okay. So that's like log n many things. And so that's what we'll do. Okay. And so that's just like one pass. And at some level, to get the union bound or higher probability stuff, we can amplify and stuff later. But so this is just kind of one pass, and it might get looped over at later on. So in one of these, you'll do one for every scale. Okay. And I'm going to fix that, and I'll say for a particular vertex, u sub I will be at the I scale, which means everything's getting sampled is probably 2 to the minus I. So F2 will be the 1/4 one, and whatever's the resulting coordinate.
Shouldn't S be mapping to R plus word or is it
This is just log n because I'm only doing one for every scale. The theorem was log square n because we could take this and then loop over another time, but we'll just analyze one pass, so to speak, first. Yeah. So there is a factor of log n not accounted for. Okay. All right. First thing we want to show is that for every index, this is a contractive map. U sub I minus V sub I is less than equal to the true distance between U and V. Okay. So why is that true? Sorry. Oh, okay. How can I use the triangle inequality? Okay, so let's say that T is the closest thing to U and S is the closest thing to V. So I'm really looking at something like d dt U minus d SV. Okay. Now what?
Yeah, it's less than DUS.
Okay, it's less than DUS because T is the closest one. Good. I think we're on our way. Now what? In particular? Okay, so I think DUV plus DVS minus DSV, is that the one you had in mind? Yeah. Okay. And these two cancel out. We're left with DUV. Okay, good. We survived. All right, so that's good. So each coordinate is not actually expanding. So that's kind of nice. Good. So now what I want to show is that okay, so there's only log n coordinates, so it's going to expand by at most a log n factor. Now I have to worry about the contracting side. And now what we want to show is that in expectation, some coordinate, the L1 norm will be at least a constant times the distance.
Where is UI? It's really for this.
Yeah, so UI was referring to the ith coordinate of the embedding. So this was a shorthand I mentioned earlier. So UI is just a shorthand for FIU. Yeah. Same with VI. Okay. So this is the opposite direction. So it won't expand too much. Each coordinate will not expand, so it can expand by almost log n. Now let's go in the opposite direction in just 5 minutes. Okay, so all right. I'm going to let delta denote the true distance. Okay. And now this is maybe the really clever part or part of it. Okay, so imagine I grow balls of certain populations around each vertex, right? How size or based on the radius, right? How many vertices are 10 feet away, 20 feet away, so on and so forth. Okay. Now for each index I, say like 16. What's the minimum radius so that the V has at least 16 vertices nearby within that radius, and U also has 16 vertices nearby within that radius? Okay, so R sub I is sort of dynamically chosen based on U and V. Okay. All right, good. Okay, and now with that setup, the claim is that for every I with constant probability, this ith coordinate is at least a minimum of Ri or delta over 2. At some level, once Ri goes across delta over 2, the balls start overlapping and they become less interesting. That's why we need this minimum delta over 2. Okay. Okay. That's the main claim. Ignore the delta over 2's for a moment. The difference between the I plus 1th coordinate is basically Ri minus 1 until the Ri's basically reach delta over 2. Why is that useful? Because the L1 norm is going to sum up all of these, right? So you're going to get like R10 minus R9 plus R9 minus R8 plus R8 minus R7 plus R6. They're all going to telescope until you get up to basically delta over 2. So you get delta over 2 minus whatever's kind of the biggest interesting R, R100, R100 minus R99, R99 minus R88. So at the end, you'll be left with like delta over 2 minus 0, basically. So you get your delta over 2. Okay, so that will telescope. That might be written out in a moment. So let's focus on proving this particular claim. Okay, so let's look at the, I think probably the more interesting case. This is where delta over 2 is bigger than Ri. Okay, so in that case, this will simplify a little bit. This will just be the Ri's. Okay. All right. Okay, so and let's say that Ri is sort of determined by U. So Ri was, as small as possible so that both balls have at least 2 to the I. And let's say that U was the bottleneck. Okay. So that means there's basically less than or less than equal to 2 to the I vertices inside U. So as small as Ri could be. Okay. All right. Now, good. Fine. And okay. Good. Oh, that means we're running out of time. Okay, so let me just make sure I do this quickly then. We only need these 2 claims and then we're basically done. Okay. So, we know that ball has at most 2 to the I, and this ball has at least 2 to the I minus 1 because it has radius Ri minus 1. This will be Ri minus 1. And we also know that they're disjoint because Ri is less than delta over 2. So these are 2 disjoint balls. Okay. Now, let's look at our random sample set S. Okay. Now, if S contains exactly one vertex from here, okay, and 0 vertices from here, okay. One sec. Now let me do it differently. Suppose I sampled one vertex from the smaller ball and 0 from none. Okay. Then I know the distance from here to here, or I'm sorry, and in general, there's some set S. Then I know the distance from here to here is at least Ri because it's not in the 2 to the I length ball. Okay. But I know that the distance from V to S is at most Ri minus 1 because it's contained in the Ri minus 1 ball. Okay. So as long as I sample none from here and 1 from here, I'll get Ri minus 1. We just want to show that happens sometimes, right? With constant probability for things to work out in expectation. Okay. Now, so P is like 1 over 2 to the I plus 1. So you're expecting to sample like 1/2 of a vertex from this ball. Okay. So you'll get none with like constant probability. And here you're expecting to sample like 1/4 of a vertex. And then the calculations are a little bit messier, but not hard compared to stuff we've already done. But you also get at least 1 with constant probability. The odds of getting none is, at most 7/8 or something. Okay. So with constant probability, you get none. With constant probability, you get at least 1. And they're independent because the balls are disjoint. So you get constant probability of this good thing happening. Okay. So you're somehow threading the needle. In the other case, it should be basically the exact same thing, except this becomes delta over 2. And this is r minus 1, which is less than delta over 2. Okay. But the same argument before, you hit 1 from here, you hit none from here. They're still disjoint because you're still looking at most delta over 2. And the only difference is that now you're going to get delta over 2 minus Ri minus 1 instead of Ri minus 1. Okay. So you do that, and then here you're going to telescope everything, and you get at least some constant times the distance. Obviously, I'm rushing a little bit, but that's the idea. Okay. So I'll let you guys get the final punchline. Well, one punchline you can just leave because you're bored. But the other punchline is, you know that it's going to expand by almost log n because each coordinate contracts. And then in expectation, you're going to get at least a constant times the true distance. Okay. And the only question is, how do I ramp this up to the stronger theorem, which is saying that for every pair, it goes up by at most log n, but bounded below by duv. Any ideas? Yeah, in particular, you're going to output the average. So you're going to take the average of log n of these, right? And one thing nice, if you want to apply something like Chernoff, you don't want any individual variable to be too big, right? So the fact that you're always bounded above by log n times the thing, it keeps everything kind of in that small contained thing. In fact, it's really a sum of each coordinate represents an independent thing, right? And each of those is less than equal to the distance. So you actually are in that Chernoff regime, and right, it doesn't matter too much. But if you apply the Chernoff bound, then you'll be happy. Okay, so it matters that every individual coordinate that's feeding into this sum is bounded above by the true distance, because Chernoff doesn't work if the variables are unbounded inside. It only works when it's sums of independent small things. Okay, all right, good. We finished only 5 minutes late, but that's all. L1 metrics are magical. They solve sparsest cuts. And in general, metric embedding is a very powerful idea. We'll do another embedding next week or Thursday.